5G is the fifth generation of cellular network technology. Term 5G is reserved for systems that meet the requirements of the ITU IMT 2020. The few notable requirements are having a download peak data rate of 20 gigabits per second, uplink peak data rate of 10 gigabits per second, and latency of 1 millisecond to 4 milliseconds. Several new technologies have been designed by the industry to meet these requirements. While it's still not clear which of this will be implemented when 5G rolls out, the 5G network that we envision uses a full duplex transmission and utilizes millimeter waves, which allows for faster transfer speeds. However, despite increasing network bandwidth, small cell towers are needed to ensure wide coverage due to the nature of millimeter waves. This then leads to a new technology known as massive MIMO, which can increase spectrum efficiency in the network. Nevertheless, the increase in cell build will clutter the horizon and increase interferences. That is why beamforming will be used to tackle the issue. Beamforming would help triangulate signals in a way which ensures that packet movements are choreographed to improve throughput as well as latency. Now that we know what 5G does, how do we use it to help the Malaysian economy? In modern Malaysia, the sea is a driving factor to the nation's economic growth as it's used in various industries, be it oil and gas, transportation, and aquaculture. However, despite it being a key factor, it could still be more efficiently used. Currently, there are over 8 ports located in Malaysia, one of which is Port Klang, which is ranked the 13th busiest container port in 2018. Now that we know what 5G can bring us, we believe that it is a necessity in improving Malaysia's economy by using 5G to realize smart ports. What is a smart port? A smart port is an automated port which uses nascent technologies such as IoT, big data, AI, among other things. The word smart also means that space, time, and other resources are used efficiently. The smart port is crucial to Malaysia's economy as it will help to automate various processes in a traditional port while also ensuring data is transferred at a quick rate to bolster processing and handling times. However, in order to make use of these technologies, a 5G network would be required to ensure fast speeds across the network. Realizing the triumphs and challenges that surround 5G is vital in enabling smart ports. So how to use 5G to enable a smart port? One example would be UGVs, also known as unmanned ground vehicles, or as you might call it, self-driving cars. These vehicles can be used to replace existing traditional vehicles to increase efficiency as well as lower cost and manpower needed around the port. However, UGVs requires hundreds of sensors to be able to handle, process, and analyze data. With a large number of sensors required, it then creates an unprecedented amount of data which requires a much faster network to process quickly, or in this case, a real-time network to process it, as even the smallest differences could possibly be what would drive or crash the UGV. The following will then consider the solutions that we have come up with to make 5G ready UGVs for a smart port a reality, while also considering the challenges the UGV would face in a smart port and how to curb them. To create a 5G ready UGV, we would have to first consider the challenges which are needed for a faster real-time network as well as a means to reduce signal interferences and deal with other challenges that can occur due to a faster network such as traffic and congestion, while also enhancing latency by reducing delay at the node of the network. To do so, we will be tackling the 5G network layer by layer. First with the network core, then the application layer, followed by transport layer, network layer, and finally the link layer. At the network core, traditionally there are two approaches, packet switching and circuit switching. The former uses a dedicated end-to-end connection from source to destination, while the latter forms connections on an on-demand manner. While arguments can be made for both ends on their pros and cons, with one having a reliable connection and the other having higher and more efficient data transfer rates, however, they are not capable traditionally for a 5G network. The ITU has classified 5G mobile network services into 3 categories, namely the Enhanced Mobile Broadband (EMBB), Ultra Reliable and Low Latency Communications (URLLC), and Massive Machine Type Communications (MMTC). The one we will be looking at is the URLLC, which focuses on latency-sensitive services such as assisted and automated driving and remote management. URLLC slicing has strict latency requirements in application scenarios of self-driving, assisted driving, and remote management. Hence, to meet these URLLC requirements, we have decided to use instead an all-cloud core over pre-existing solutions. This would mean that a network architecture based on data centers will be formed, in which all functions and service applications are running on cloud-native architecture. Hence, this would provide logical independent network slicing on single network infrastructures to meet diversified service requirements, provide DC-based cloud architecture to support various applications and scenarios, while Recurrent selecting radio access networks RAN to provide massive connections to be implemented in an on-demand manner to meet 5G requirements. This means that a simplified core network architecture will be used to implement on-demand configurations of network functions through control and use per panel separation, component-based functions, and unified database management. At the application layer, currently there are two approaches that exist: the peer-to-peer and client-server approach. The latter focuses on information sharing, with data management centralized, while the former focuses on the connectivity of remote computers where each peer is its own data center. However, again, these aren't suitable for our 5G smart port as well as the UGVs we plan to implement them. So instead, relating back to what we mentioned in our network core, where we use an all-cloud core, here we will be using a similar system where the UGV communicates with the other parts of the port, in which information is collected or stored as an alternate measure. However, otherwise we intend for each UGV to have its own data center installed in it, only for crucial information storage. This is to ensure that there is no delay in data processing and the actions are carried out in real time to avoid collisions. Therefore, rather than choosing a normal client-server system where issues like bottlenecking occur due to the need of servicing multiple clients, as well as the distance and signal interference to cause a higher chance of packet loss, we instead implement both, in which UGVs use either modes situationally as per given for cloud-native core. This would help avoid issues with a usual client-server system, especially in a port, such as a signal loss due to the nature of a port, as well as a lower load on the server side of the system by implementing peer-to-peer as well as countermeasure. For the transport layer, once again there are two main approaches, TCP and UDP. And in similar fashion, current models of both the protocols are not suitable for 5G, and instead we have decided to use a hybrid version of TCP. TCP is concerned with reduction in packet loss, and thus is able to reliably transport information from the sensors on our UGV to relevant clients. On the contrary, while UDP is said to be most suitable for real-time application, however, due to the nature of its protocol, packet loss is a possibility, and a very high possibility, in a port due to all its containers, weathers, and other such challenges. This is a definitive issue, as UDP does not consider itself the receiver is able to receive all the information, but for UGV to carry out its duties accurately without causing structural damage in the port, packet loss has to be kept at the very least at the minimum. While TCP has its flaws, such as non-equilibrium network, these issues can be solved using congestion flow control for packet loss, slow start algorithm, and round-trip timing. However, TCP alone is not a 5G ready protocol, and hence we opted for using the TCP New Reno, which is the improved version of the TCP Reno, with its ability to detect multiple packet loss in comparison to its predecessor, ability to only detect a single packet loss at a time. For this layer, we have made it as a combination of layer 1 and layer 2, the physical layer and link layer, which is also known as Open Wireless Architecture, OWA. OWA is the combination of different access technologies as cellular, cordless, wireless LAN type systems, short-range wireless connectivity, and wired systems on a common platform to complement each other in an optimum way for different service requirements and radio environments. To ensure that information travels fast, the routing algorithms used here is Dijkstra's algorithm. Dijkstra's algorithm is an algorithm for finding the shortest paths between nodes. While there are limitations in its usage, we'll be implementing a more refined version of the algorithm as testing is done. This is to ensure that our algorithm is constantly updated to adapt and overcome to the needs of a smart port. For the network layer, we have decided to implement a technique known as network slicing. Network slicing is a virtual network architecture that uses the principle of software-defined networking and network function virtualization. We have decided that it's a necessity for 5G smart ports and to tackle our specific problem of UGVs because it allows multiple virtual networks to be created on top of a common shared physical infrastructure. In this case, the network will be sliced into multiple virtual networks that allow support for different RANs. Thus, network slicing is important because of the multitude of use cases and services that our smart port will need to support aside from our UGVs. For example, a UGV relying on communication requires low latency and high throughput, but this is because real-time information exchange from one UG to another to dependent routing on another port will require high throughput and might affect latency. To ensure that both a high throughput and low latency is maintained, network slicing will be able to ensure both requirements over the same physical network using a virtual network. ultimately optimizing the use of the physical network. Therefore, it can be said that network slicing would allow 5G to be more efficient by maximizing its flexibility and optimizing both the utilization of the infrastructure and the allocation of resources in the network. Thus, this would help enable much more efficient usage of energy and cost compared to a 4G network, ultimately making our UGVs the safer, smarter, and more efficient choice. There are also other challenges that we have to face when it comes to implementing a 5G network and particularly having UGVs in the smart pod, which is signal interferences. Due to massive MIMO that will be involved in constructing this network, there will be high densities of information being passed through the waves, and given the nature of the pod, as well as other external factors like weather conditions, signals can interfere with one another and cause loss in information. Hence we have decided to implement a technique known as beamforming. Beamforming is a technique that focuses a wireless signal towards a specific receiving device instead of having the signal spread in all directions from a broadcast antenna. This ensures faster, more reliable, and more direct connection. To put it simply, signals will be directed rather than simply sent sporadically towards its target destination in hopes that it will reach, thus ensuring that routes are more efficiently used and reduces overlapping among signals. Therefore, by using this method over traditional methods, we could avoid signals being blocked by containers in the pod or cause interferences due to overlapping with other signals. Ultimately, this ensures that UGVs would be able to carry out its tasks while maintaining communication between other hosts in the smart pod's network. And to conclude, what we have discussed today is how we would like to adopt 5G to boost the Malaysian economy by creating smart pods which are powered by this next generation network. Particularly, we discussed how UGVs will be a staple in creating this smart pod. And to enable UGVs, we then talked about new technologies that 5G would bring, such as millimeter waves, beamforming, and various other technologies, while also covering the challenges that we would face in making this a reality.